Good morning. I'm Prabha, Assistant Professor of Chemistry, PBM Research Department of Chemistry, A.D.M. College, Autonomous, Nagapattinam. Today's class we shall discuss the perturbation theory and its application to the first order wave corrections as the derived equation from the perturbation theory that has been taken to define the approximations that are given. So as the perturbation theory from the unperturbed state, how approximations are made to define the wave functions, which are the first order wave corrections, and as well as the energy corrections that are implicated, so as to define the perturbed system, or in other words, we say that which is a solvable Schrodinger wave equation is used to deduce the unsolvable Schrodinger wave equation. In other terms, also can be understood as we are moving from the harmonic oscillators to the unharmonicity. How it is possible that we are approximating the wave functions and the energy functions or the eigenvalues such that those becomes defined and solvable. So the first order wave function corrections, let us see to now. The theory that has been the perturbation theory, where we used up the equation that has been deduced previously. So here, to define the system, h cap of 0 represents that for the Hamiltonian for the unperturbed system, and psi of n, the wave functions with corresponding first order correction, and E of n, the eigenfunctions, which corresponds to the unperturbed state because E of n of 0, and again here the other term which is referred by h cap of prime. H cap of prime here represents the phenomenon of perturbation, and perturbation h cap prime is nothing but the difference between the Hamiltonians of the unperturbed state and the perturbed state. So now let us apply that, or as we define psi, the wave function, that psi is defined as psi tending to psi of m, its conjugate. Then correspondingly, the wave function can then be represented as psi of m. So under the conditions, let us implicate the conditions that m is not equal to n. In that cases, it follows that we'll be defining or we'll be applying the equation E of psi is nothing but h cap of psi. So here E of psi, instead of that, we will apply that corresponding to the wave functions of m and n, and hence the eigenvalues become equal to E of m of 0 and correspondingly E of n of 0 for the corresponding wave functions of psi of m and psi of n. Thereby, these terms as for the eigenfunctions and the corresponding conjugates or the multiplicates, not the conjugates, here it is the product multiples of two wave functions, which will be as psi of n, which means that the wave function corresponding with the first order corrections with that of psi of m of 0. Psi of m of 0 representing the wave function corresponding to the unperturbed state, because we have defined the system that it contains psi of m and psi of n. And in under the cases that m not equal to n, then what approximations can be done based on the perturbation theory or the first expression that we have put it up here, such that it is possible to define the wave functions, and that implicates that as first order wave function corrections. And now here this becomes equal to the negative functions of psi of m of 0, or in other words, that the Hamiltonian systems for the perturbation. So the Hamiltonian for perturbation is represented by h cap of prime. So h cap of prime, that is acting on psi of n of 0, corresponding wave functions of psi in its unperturbed state and corresponding wave functions of m in its unperturbed state. So that becomes equal to the factor that which we have defined so far. Now let us apply the expansion series and introduce the expansion coefficient. So from this expansion series, we are able to deduce that solvable part, and that approximations have been made such that it represents the true wave functions, or if it is applied to the energy cases, it implicates that it represents the true eigenfunctions and also the eigenvalues. Eigenfunctions obviously will implicate the wave function correspondingly because it satisfies the conditions there. And now let us apply that with having to define the expansion coefficient. So that expansion coefficient, let us see to the equation that is represented here. What the equation suggests here, psi of n of 1 can be now defined such that It is a summation series of m, a of m, the coefficient, and the correspondingly the wave function that corresponds to the unperturbed state. That will be nothing but psi of m of 0. So psi of m of 0 and its corresponding expansion coefficient summation series will be now, or that will be now representing, or that will be liable to represent the first order wave correction state. Having deduced that expression, let us now apply it up here in the previous expression of 1. So that gives the energy expression being now defined in a way, and rearranging the expression, we will be able to deduce what the value of the expansion coefficient is. So in the expansion coefficient, that will be given by the perturbation is acting upon two wave functions, and first it is acting upon the wave function of psi of m of 0 state, psi of n of 0, and then as a product multiple of psi of m of 0. This equation, as it corresponds from the previous expression, and it is since a negative term, the rearrangement of the terms that makes it up in the denominator term, the eigenvalues. The eigenvalues that will correspond to E of these terms get rearranged such that inversing the negative signs. Thereby, you will be able to define the expansion coefficient. Having defined the expansion coefficient, let us substitute in the primary equation, which is the first equation previously given there. And now, having substituted, that will define psi of the system, or in other words, psi of n that corresponds to the wave corrections that is being implicated. So, how will we be able to define psi of n of 1, or in other words, as psi of n will be nothing but the basic wave function plus the summation or the corrections terms that has been implicated by deducing the values of E of m. So that will imply that as psi of n tending to, or that becomes equal to psi of n of 0, which means that the wave function that corresponds to psi of m and under its unperturbed state, that has to take it up the summation values of, under the conditions that we have first implicated and deduced, is m is not equal to n. Under those cases, that becomes equal to perturbation is acting upon psi of n of 0 and then on psi of m of 0 divided by En of 0 minus of Em of 0. So what these values become? Perturbation acting upon the wave functions corresponding to the nth state in its ground. Here 0 doesn't mean the ground state at all. Here it means it's an unperturbed system. And psi of m, again, that wave function corresponding to nth state and its corresponding unperturbed state divided by the eigenvalues, and corresponding basic wave function has to be taking its product multiple, which means that this summation factor, as has been deduced from A of n, has to be now multiplied with the basic wave function, which is nothing but psi of m of 0, which means that psi of m corresponding to its unperturbed state. So this summed up parameter will now be able to define the true wave function, which is nothing but that first order wave function corrections that we have implicated in this equation. Thank you all.